Like you learn topology, you learn node voltage equations, you learn mesh current equations from your previous classes as well. So you should be a master of those topics already. I really want you to practice those concepts, because we will be building on those concepts in the next topics, and then it will get more and more complex. So if you solve any issues about those topics now, that will be very helpful for your success in this class. So one nice thing I need to say is all those analysis techniques, especially those simple node voltage and mesh current analysis techniques, will be directly applicable to circuits with inductors and capacitors. So up to now, like most of the circuits you were dealing with had only resistances, like sources, of course, but mainly the components that we were dealing with was resistance. And then we were relying on Ohm's law. Everything was easy. Actually, everything will still be very easy for you, but we will just add different components, and we will try to analyze their behaviors as a part of a circuit, complex circuit maybe. So for this course, I think we will be talking mostly about inductors. If we have time, we will also switch to capacitors. So that will depend on how much time we have. There is one thing common that we should first talk. These are passive components. So passive means in terms of electricity, you cannot generate electricity with these components, so you cannot generate any power. But one nice thing about these inductors or capacitors, unlike the resistors, they can store energy. For example, when you have some energy in the circuit, you can store them on an inductor or on a capacitor. Then whenever you need, you can take them back, so that like you can temporarily put your energy into these components, unlike the resistors where you can't really do this, like they will just dissipate the energy. So you can store them inside like capacitors, and then you can take it back whenever you need for another task. So that is something very very important, and we will be relying on this concept a lot, especially in your next courses in this department. You will be relying on these concepts a lot, that storing energy in these components. So let's just start with an inductor. I hope you can clearly see the node screen. So inductors, I can just plot a circuit symbol for an inductor. So this is how we represent an inductor. This is just a component that you will be placing somewhere inside your circuit. So that will depend on how you want to build your circuit. So for inductors, we generally represent them with L. So this is the very common symbol for an inductor. This is a global notation, so please try to rely on this notation as much as you can. Again, just like resistors, there will be a voltage drop across the terminals of these inductors. And again, as I said, we will be relying on terminal behavior on these components. And then, of course, there will be some current passing through this inductor. Actually, it will depend. We will talk about this. So when they won't allow any current to pass. So this is a very simple but general description of how an inductor will look like. And then when you had the resistors in this scenario, for example, we were representing them with the letter R, right? And then we had the unit for the resistance of that resistor. So that was ohms. Does anyone know the unit for an inductance?
Henry's, I think.
Henry.
Yep. So this is the name of the guy who invented this. So the unit for inductance is Henry. So we will generally say like 3 Henrys, 2 microhenries, 5 millihenries. So you will be hearing this unit a lot. So that is the unit of inductance, the amount of inductance for this component, let's say. So, and for the other things, of course, you know the unit. So for the voltage, we know this is volts, right? And then for this current, we know the unit is amperes. And then we have time, of course, there will be a relation, time relation. So that will be seconds. And then I don't know if we missed anything, but I think that should be all. So in the case of resistors, we had a unique relationship which described current voltage relationship between, not between, current voltage relationship of a resistors. Right? We were calling that thing as Ohm's law. So we were saying there's a very nice, for let's say for a resistor, oops, for a resistor, we had this very nice voltage current relationship, right? So now we really need to generate a similar, say a similar relationship for voltage and currents of an inductor. So this is not as simple as in the case of resistors, but of course it's not really a big issue. So in the case of an inductor, the voltage current relationship will be written as V equals L times EI over dt. So here you can see the way your current affect your voltage drop on this component depends on the rate of change in the current. It's not directly dependent on the current itself, the magnitude of the current, but it depends on the change on the current. So if you try to focus on this equation, you can imagine like the intuitional functionality of this inductor. So since you are only having a voltage drop here when there is a change in the current, right? So basically, I can simply say that if there is a constant current, so let's say if I am applying a constant current, what is the voltage going to be?
Nothing, zero.
Yes, exactly. So if there's a constant current, its derivative will be zero. There is no change. And then basically the voltage across the terminals of this inductor will be zero, which means that this inductor will be short-circuited, right? This is how you can understand how this component will react to the changes in your circuit, to the changes in the current or voltage in the circuit you are working on. So that is something very important, and of course, at the same time, like this is like, if you again focus on this equation here, this is like the voltage drop will occur here based on the magnitude of this magnitude of the change of current here. So it's like you will be having a component here which will try to resist changes in the current. So it's like it's trying to stabilize the changes in the current, because based on that change, it will create a voltage drop here, right? So that is something very important. And then this equation also brings something very important, which is you cannot have an instant change in the current, right? So imagine, let's say, imagine an instant change in current. So it's like it's not physically possible, but imagine you suddenly change the current from 2 amperes to 5 amperes. What is going to happen? So you have a switch, you just, like, let's say, you just double the current flowing through the terminals of the inductor. So can you guess what is going to happen?
Voltage drops, maybe.
Like, okay, like look at this equation. And then imagine you're doubling the current instantaneously.
High voltage maybe. Or
yes, there will be extremely high voltage, and actually if you're trying to write this mathematically, so an instant change here means that this will be infinity, right? So that derivative will be infinity because there's an instant change in basically zero amount of time. So in that case, So this will be, well, let's say, it's better to write it in this way. Let's say instant change here. So that will yield infinity, an infinite voltage here, which is not really possible. So basically, if you try to instantaneously change the current, this inductor will resist to it by creating an infinite voltage drop. Basically, it will be like an open circuit component here, which will not allow the current to pass. So it's like it won't allow that instant change to happen. So it's like it will filter this. We will later see the characteristics of these components, I think in ELE 220 course. But for now, what we should know is if you are trying to apply a constant current, then this will behave like a short circuit. Like there will be no voltage drop across the terms of the inductor. That current will directly pass through the terms of the inductor. But if you're applying if you're trying to apply an instant change in the current, that won't be possible because the inductor will block it. Because mathematically that will correspond to infinite voltage, which was not really possible in our theoretical analysis. But you should remember something. This is not possible in a physical system. Like you cannot make a current, change the current from 2 amperes to 4 amperes instantaneously. So there should be a tiny bit, even if it's like tiny bit amount of time, where this derivative will be a number, like a non-infinite number, like a finite number, let's say. So, but of course, that number will be very huge. There will be a huge voltage spike, which is not again possible. But so we should say that this is not something we can physically implement. But of course, we can make that duration extremely small so that we'll be having a finite but huge voltage change. Right? Okay, so this is the very basics of input-output relationship or current voltage relationship of an inductor. Let's just work on a very simple example so that we can try to understand this this current voltage relationship. So I will be just trying to plot this graph of I think this is a graph of a current across the terminals of an inductor so that we can try to calculate the voltage drop across time given this current. So that is, we'll try to plot this axis as fast as I can. Okay, and then let's say this is 1, this is -1, this is 0, this is 1, 2, 3. I hope it's equisampled. And then we have time here. This is time axis, which is in the units of seconds. And this is our this y-axis is our current. This is with the units of amperes. So let's say this is the current profile we are applying to this inductor. So that goes all constant all the way until 2, and then it drops back to 3. So imagine this is the current function of current with respect to time for an inductor. And then let's say this inductor is 3 Henries. Can someone help me to plot what the voltage graph will look like? So by the way, I should write this equation also here so that we can remember the relationship between the current and voltage. Is there any volunteer that can help me to plot this? So I will just try to put this graph like lines here so that we can use it when we are trying to plot. Okay, now I need a volunteer.
I can help you maybe.
Of course. Can you say your name, by the way?
My name is Emirhan. Emirhan is.
Emirhan. Okay, Emirhan. Okay, so for this one, what I would like you to do is to look at this graph for like we have different sections here where the current has different characteristics. So we should analyze this part by part, like region by region. So can we start maybe from this -1 to 0? So what this, how the voltage will look like in this region?
There is a positive change, so di per dt is equal to, I think, 1. So the voltage is 3h time 1 and 3 volt.
Okay, so you're saying from -1 to 0, di over dt is 1. So basically in this region, the voltage is 3 times 1, that is 3 volts, right?
Yes.
So you're saying the voltage will be constant here.
Yes, I think.
Okay, so let's say this is 3 volts. So what Emirhan is saying, if I take the derivative of this current graph here in this region from this -1 to 0, so it has a constant slope. So and its derivative is positive because it's going from 0 to +1 in 1 second. So it's like the change is 1 amperes, duration is 1 second, so that will be 0. That will be 1. And then if I multiply it with the inductance, which is 3 henries, so we will be having this constant voltage line here, right? Okay, Imran, what is going to happen next?
From 0, we don't have a change in the current, so there is no voltage, I think. From 0 to 2 seconds.
Perfect. So from 0 to 2 seconds, Imran is saying di over dt will be 0. Basically, P will be 0, right? Because there is no change in the current. So let me do this so we can see the graph. So we will move here, and then I will be saying there will be no voltage from 0 to 2 seconds, right? Perfect. And then what happens? In the last 1 second, from 2 seconds to 1 second.
And then we have a negative change in the current, so I think we have negative current, a negative 3 volt.
Okay, so from 2 to 3, di over dt is -1. So basically, voltage is 3 times -1, which is -3 volts, right? So here in that case, we will be having a constant -3 volt change here. So what's the -3 volt voltage here, right? So let's also label it right here. So that would be -3. And I know this here so that if I share these notes, you can see them on the same page. Okay. So thank you, Imran, by the way. So if you look at this graph now, like this is really simple to generate. I believe that all of you can easily generate these kind of graphs. Like when you see this current plot, you can immediately draw the voltage plot. But you should just calculate the current voltage relationship 1 by 1 for each region, and then you will plot them. It's extremely simple. But there is one thing I want you to notice here. It's some nice feature. So we said, I think somewhere here, you cannot have an instant change in current, right? Like this is not really possible because you will be having an infinite voltage. But if you look at this plot, although we cannot have an instant change in current, we have instant jumps in voltage, right? So you should always remember this. So in an inductance, although you cannot change the current instantly, you can change the voltage instantly. Basically, again, those instantly terms are not like a little bit vague, but you should theoretically understand the difference between the instant change in current and non-availability of an instant change in current. But you will be observing an instant change in the voltage, right? But this is something I really want you to focus on for now. Okay, so let's continue from this topic. So up to now, what we said, so we wrote this beautiful relationship where we said the voltage current relationship is V equals L times di over dt, right? But if you look at this equation, so it's like it assumes that basically we have the current, so we can take its derivative, multiply with inductance, and we can calculate the voltage. But what if we have the voltage and we are asked to calculate the current? So this equation will not be directly useful in this form to do this reverse calculation. So we should play this with this equation a little bit so that we can find like basically an analogous inverse equation that will allow us to calculate current given the voltage, right? So let's try to play with this equation a little bit, as much as we can. I will try to work as clearly as possible, but again, if you feel uncomfortable with any steps, just stop me, we will discuss. So first of all, I will make a change here. So I will say, like just for notation, we were dropping t's, but I think it's time to put them back here. So what I only did is I added this t's times here because that voltage and current depends on time. Actually, that is also the case here, like everywhere. So like the graph of this current and voltage depends on the time. So these were time axes, right? So now I just plugged in back those variables so that we understand that when you are taking derivatives or integrals, those t's are meaningful because you should know which parameters your variables depend on, right? So in this case, what I'm going to do is I will multiply both sides with dt just to simplify the equation. So I will say if you multiply both sides with dt, so let's say multiply both sides with dt. So what we get is vt times dt equals to L times di over dit, right? So basically that is a very simple. That's a very simple case. So in this scenario, now I will take integrals for both sides. So this this t will not be meaningful here, but you should know that this current depends on integral, but the parameter of this integration component, like this di, that thing will depend on I itself. So if you're trying to take, for example, derivative with respect to time, so you should apply something like a chain rule. You will be taking derivative with respect to current and then taking derivative with respect to t. But for now, for our equation, this will depend on di itself only. So now what I'm going to do is I will take integral, but this integral will depend on dt here. So basically, it will depend on time here. And then it will depend on current here on the right-hand side. But of course, I know that current also depends on time. So based on the analysis we are dealing with, we may need to modify this a little bit. So now what I need to do is I will make some changes in this equation so that I can include the bounds for this integral. So we should decide where we are going to start. Like for example, this side, and for the left-hand side, this depends on t. So we should define the initial time, and we should define the final time where we're trying to calculate. So basically, the initial time can be anything. Like I can just say t0. So this is just an unknown number. So we will start from t0, whatever that t0 is. Generally, typically, let's say it's 0. T0 is so basically like you start the time from 0 seconds, but we can keep this parametric. We can just say the lower bound of this integral will start from t0. For the upper bound, I can just say t. So I don't need to calculate this until a specific numeric time. I can make it parametric. I can just say t. So whatever time you want, you can just plug it in and calculate your result. But of course, when I put, so let's say, when I put t0 and t here, I don't want this dt to be confused with this t here that I am trying to calculate up to that t. So I will be replacing these t's here with maybe vy. So I will just rename those variables because they're just the parameters of this integration, it really doesn't matter at all. So I will be taking this integral of this vy dy, and then I will be calculating it from t0 to t, right? And then for the right-hand side, so that L doesn't depend on anything, so I can just take that directly out. And then here, this side of this equation, now this integral depends on current. So I should define the initial and final values in terms of this current. So it's like we said for the left-hand side, the time will start from t0. So basically, I should say I will be using the value of the current at t is equal to t0. And then I will calculate this up to I of t, basically the current at t0. But again, I don't want to confuse myself with using the same symbol I for the bound and the integration parameter itself. So I will just change this with dx. So whatever the result of the integral, I will be plugging in these bounds. And I know from your math classes, you're an expert on this type of simple integrations. You can do them extremely fast whenever you have the problem itself, right? Okay, so let's now try to calculate the result, right? So for this part, it's not really directly obvious because we don't know the like for this left side, we don't know what this Vy is going to look like. So we will be having a function of time for the voltage that can be just like these graphs that we had before, right? So this is a little bit ambiguous for now. We can't directly calculate this integral, so I will leave this integral as is. I will just say whenever we have that voltage equation, we can calculate that integral. But if you look at the right-hand side, it's just dx. There's no function here. I can just take the integral of dx, which is going to be x. It's that simple. So for this side, as I said, I will be, I can just swap the sides. That will be more easier for me. So the integral of dx is x, and I will be evaluating that at it and it0, right? So that will be equal to integral from t0 to t vy dy. And then I can calculate this left-hand side again. I can say L times, I can first actually take this L to the left-hand side, right? So I can divide everywhere with L. So that will be 1 over L. And then I can say the left-hand side will be it minus it0 equals 1 over L times t0 t vy dy, right? And then, so this is the initial condition, like this this thing here is the initial condition. So basically, that should be known. I should know the initial condition of the current so that I can calculate the rest. So I will take this to the right-hand side. So let me fix this equation in this manner. So I will be just saying, so that was minus here, so it will be a plus here, right? So this is how my voltage current relationship will look like. So this is just the reverse of this equation. So we were saying Vt is L times di over dt, right? So now these two equations, by using these two equations, I can do the transitions from either from like current to voltage or from voltage to current very easily when I know, of course, the initial conditions. But of course, the initial condition only matters for this current equation. For the other equation, that if there is an initial condition, it will automatically drop due to time derivative. Like that constant initial condition will go away. But for this voltage to current calculation, you will need that initial condition. So it will matter a lot. You should be paying a lot of attention for those initial condition calculations, right? Again, in practice, people generally, let's say, chooses t0 to be 0. In that case, that lower bound will be 0. Like this this lower bound will be 0. And then, of course, this thing will also be 0. So those two t zeros will be equal to 0. But it depends on the application. Sometimes it's not really that case. Okay. Is there any question about this formulations, these equations we generated today? Anything you don't feel comfortable about calculating these components? Is this all clear for everyone? Can someone say something?
It's clear to me.
Okay, thank you. So that would be great if you respond and like some of you at least respond so that I can still know you exist there, because I don't see anyone and sometimes even like the connection drops, we can't even understand. So that is really helpful if you say something. Okay, so let's use these two equations on an example so that we can have some practice. So I will be writing an example here. So let's say what is it says L is 2 Henries. Again, remember the unit. And then it says Vt is 6 times 5 cosine, no, 6 times cosine 5t volts, basically. And then the question is, find IT if T0 is minus pi over 2, and then the initial current at T is equal to T0 is 1 amperes. Okay, so now the question is, we have the function, time-dependent function of voltage, and we are asked to calculate the current. So if you remember our beautiful equations, basically we will be using this equation. And then we are given the initial time, so that is great. We are giving the initial current value at that time, so that is great. I think we have all necessary parameters here to implement this function here, right? So I will be just plugging them in and calculating the result. It will be very fast and very simple actually. So let's pick another color so that you can see the solution. So we know our current is going to be 1 over L times integral from T0. Basically that T0 is minus pi over 2. I can just put it in here, right? And then that will go until T. And then here, Vy is 6 times cosine 5t, so that I will just put 6 times cosine 5y so that I don't confuse it with t. And then we will be having Vy dy. So I'm trying to remember the equation. And then we will say plus the current, the initial currents, which is 1 amperes. I know it already. So that is 1. And then actually I also know L, so I will be replacing this with 1 over 2, right? And then the rest is just calculating this integral. The rest is not really about circuit analysis, but of course, we are responsible for doing these calculations in exam. So I will be conducting the calculations so that we can find the results. So let's try to do this as fast as we can. So this is I of t. I can take the 6 out here. So that will be 6 over 2, which is 3 times minus pi over 2 to t cosine 5y dy plus 1. Okay, what is the integral of cosine 5y dy? So I need a volunteer to help me. What is this integral?
Sine 5y over 5.
Perfect. So that is sine 5y over 5. And then I need to evaluate this from minus pi over 2 to t, right? So I can take that 5 out. That is like, that will be 3 over 5. I think that will be just 0.6, right? And then for this inside, I will be having sine 5t minus sine minus what, 5 pi over 2, right? please double check these calculations. Okay, I think that would be correct, but can someone calculate this part? So that should be a constant number. It's just sine of something, and 5 pi over 2 is a number, right? So can someone calculate this number for me? What is sine minus 5 pi over 2?
Minus 0.1.
Minus 0.1? Are you sure?
Yeah.
Is that minus 1?
Let me calculate. So this is 5 pi over 2. Sine is periodic over 2 pi. So this is equivalent to, that is equivalent to sine minus pi over 2, right? So sine is 0 at 0. At pi over 2, positive pi over 2, it's 1. So that should be minus 1, I believe, instead of minus 0.1. Can you double check this? I don't know who said this, but that would be great if you can double check. What I think is this should be equal to minus 1 instead of minus 0.1.
I used calculator.
But
Okay.
you have to use it in radians.
Yes, please. That is one thing extremely dangerous. And that will be failing you in exams. And really, believe me, no one in this department will be forgiving that simple mistake. You can say like, that's just a tiny bit of mistake.
You are right.
But never do this mistake. Right? It's extremely critical. As engineers, the units matter a lot. Like the first thing I said about inductance was, if you remember, was like one of the first things we taught was like those units matter a lot, and no one really will forgive this in this department. This is extremely critical for your development. Okay, so now, do all of us agree on minus 1?
Yes.
Okay, perfect. Then let's do the rest of the calculations. So that should be now. So from here I have 0.6 times sine 5t, and then so that will be plus 1.6. So that will be like, I think 1.6 amperes, right? So now I think this is our solution. But please also don't just trust on my calculations, and of course your own calculations. Just double check those things, both for practice and to make sure that you make the right calculations. Okay. So this is how we can calculate the current given the voltage equation. It's if you really focus on what is going on here, it's most part of this is from your math class. It's basically math. We're just trying to use some equations that we again generate based on math. But we all started with this very fundamental equation right here. It all started with this equation here, right? So it's like when we know the relationship once, the rest is just applying math. So you should be extremely fast to gain time in your exams, especially. But you should also be very careful when doing those calculations, because those are not the parts of this course. But of course, you should be getting the right answer in your calculations. So you can just say, I made a unit mistake, and then now the building I did